Hello students, today we will learn that what is a draft tube and what is its purpose and what is draft tube efficiency. I am talking about the draft tube which is generally implanted over the exit of Francis or Kaplan turbine, which are the two types of hydraulic turbines. So over here you can see a Francis turbine. So what happens? From penstock water comes and flows in the casing and ultimately guided by the guide vanes. This is the guide mechanism, and radially goes inward. So over the center there is a runner. So when water hits the runner, then it develops force over the blades of runner. So it develops torques and in turn develops power over the shaft. So ultimately water which is collected over the center is made to exit in axial direction. So over the exit there is a draft tube implanted. You can see over here this draft tube is connected to the central exit of this Francis turbine. The same type of draft tube is implanted on Kaplan turbine also. But what is the purpose of keeping this tube? Water can made to go out from the system without any such type of tube, because ultimately when water has done work, then it shall exit out. What is the purpose of this draft tube? In case we are not keeping the draft tube, still the water will go out. What is the purpose? That we will understand. Okay, so over in this picture I am showing that suppose water is coming and interacting with the rotor. This is the rotor of hydraulic turbine, and then ultimately exiting from the center and going in axial direction. Suppose a piston cylinder system is implanted over the exit of this hydraulic turbine. This piston is of heavy weight. Suppose the weight is W. Now in case piston is free to move under action of gravity, then it will pull the piston in downward side. So what will happen? Over the top a negative pressure will be created. Piston is moving downward side, so the force is developed over the piston in downward side due to action of gravity. So over the top side a negative pressure is developed. Okay, so what will happen? That the pressure difference between the 2 points over the inlet and over the exit will be more. In case we are not using this piston cylinder system and water is made to go out without any such mechanism, then in that case over the exit of this machine the pressure would be 0. But in case this system, this piston is applied, then the pressure over the exit of this runner will be lesser than 0. So ultimately the pressure difference will increase, because P1 minus P2 is equals to P1 plus P2. So this is what the benefit in case we are implanting a piston cylinder system over the exit of this hydraulic machine, and piston is of heavy weight. And the benefit of greater pressure difference between the two ends, that is over the inlet and the exit, is the pressure difference is responsible for making the water to flow through the system. So greater the pressure difference is, greater the amount of work done can be developed over the rotor. Now imagine, see, this is the piston. Suppose it is made up of metal, heavy metal. Now in case the same piston is made up of water, then also the same effect can be produced. Okay, so this is what the principle of draft tube is. Okay, so in actual case the draft tube is a sort of duct, and it is sort of diverging duct. Okay, so what happens then? When water comes out from the exit of this runner, then it flows through the draft tube, and the same mechanism over here, as we are talking about this water piston, same here. Water when moves downward, then it creates a negative pressure over the exit of the machine. So greater pressure difference between the inlet and outlet can be obtained, and it leads to greater amount of work done over the runner. In case we are not using draft tube, then still the runner will work, but the amount of work done will be lesser in that case. So draft tube enhances the work done developed over the rotor. Now what is the reason of this diverging type of draft tube? Actually, suppose over the exit of the runner the velocity is v1. Suppose water is entering this runner with velocity v, and coming out with velocity v1. So what happens? That v1 means it is having kinetic energy. So when it moves through this diverging draft tube, then we know this thing, that in case we apply the continuity equation over the inlet and exit of draft tube, then a1 v1 equals to a2 v2. Since over the exit the area is larger, so velocity will be smaller. So in that case what will happen? by Bernoulli principle, in case velocity decreases then pressure increases. So what happens, this entire kinetic energy which is there over the exit of this runner will convert into pressure energy at the bottom. So over the bottom pressure will be more, on the same behalf over the top pressure will be less. Same as, suppose this is the heavy piston, so over the bottom it is applying force, so over the bottom there is pressure, positive pressure, but over the top side there is negative pressure. So more the positive pressure over the bottom of the draft tube is, more the negative pressure will be developed over the exit of this runner. So the need of draft tube is that it will decrease the velocity as compared to that of exit of this runner, and in turn will increase the pressure, and that is that happens spontaneously by Bernoulli's principle. So more pressure at the bottom and less pressure at the top will be developed then. Now let's apply Bernoulli principle over the two ends of the draft tube. Suppose this is the draft tube and this is point 1 and ultimately the point 2. So the draft tube is ending over a reservoir. This reservoir is called as tail race. Okay, so this is the level of tail race, level of water in tail race. So this is what the technical end of the draft tube. Okay, so this is the level up to which the water is flowing. This is the level up to which water is considered to be flowing from point 1 to point 2. Okay, now at point 1, suppose the pressure is P1, so P1 by rho g is the pressure head. Suppose velocity is V1, then V1 square by 2g is the kinetic head. And we know this thing that in case we are choosing this dash line as datum line, then this point 1 is at a height h, capital H. So therefore capital H is also there at point 1. So total head at point 1 is equals to P1 by rho g plus V1 square by 2g plus capital H. Now at point 2, suppose pressure is P2, then P2 by rho g is the pressure head at point 2. Similarly, suppose V2 is the velocity at point 2, then V2 square by 2g is the kinetic head, and HF is the head lost between the point 1 and 2. So means when water flows through this draft tube, then practically due to frictional effect some amount of head will be lost. It means like this, that this is the total head available over the LHS. I am taking the total head available over the point 1. At point 2, ideally the head must be same. The head at point 1 and at point 2, the head must be same by Bernoulli's principle. But since some amount of head is lost, that is HF, so that is also taken from the head which is available at point 1. So the total head at point 2 plus the head loss is what equals to the total head at point 1. So this is how we have applied the Bernoulli's principle. Now at point 2, what is the pressure? Since this is the datum line, so at the datum line over the outer water surface, the only pressure acting is atmospheric pressure. So that is what acting over the point 2, because level is same outside and inside. So PA is the pressure at point 2. So in place of P2 we can write PA. Okay, now keeping P1 by rho g over the LHS and taking all the entities over the RHS, we are getting this equation. Okay, you can see P1 by rho g equals to PA by rho g plus V2 square by 2g minus V1 square by 2g in the bracket minus H plus HF. Now in case we multiply both the sides with rho g, what we will get? P1 equals to PA minus V1 square by 2g minus V2 square by 2g inside the bracket plus H minus HF into rho g. Now over here we know this thing that V1 is greater than V2. It is because over point 1 the area is lesser compared to over point 2. Applying continuity equation, A1 V1 equals to A2 V2, V2 will be smaller than V1. So definitely this number is positive. Similarly, this head H is also taken as positive, and the value of HF is generally lower than the addition of these two entities, means V1 square by 2g minus V2 square by 2g plus H. The value of these two addition is always greater than, generally is greater than HF. So definitely this quantity, this entire quantity inside this square bracket is positive, because this density and acceleration due to gravity is always positive. So this entire entity which is subtracted from PA is positive. So definitely from atmospheric pressure, if some amount is subtracted, then at point 1 it means the pressure is lower than atmospheric pressure, so that is vacuum pressure. So this is how the draft tube develops a vacuum pressure over the exit of the runner system. Okay, now what we see over here, in case we are taking this equation, that we need more and more vacuum over point 1, means as less the P1 is, more amount of work done can be available with the runner. So we need P1 as less as it could be. Okay, in this runner at point 1 the velocity is v1. Okay, so what happens, that whatever the exit velocity is, that is a constant. Okay, now the height of draft tube is also constant, that is capital H. Okay, now Pa is the atmospheric pressure, that is also constant, that we know that it doesn't changes. Okay, so the entities which will responsible for decreasing the P1 is actually V2 and HF. Means in case V2 becomes 0 and HF doesn't exist, in that case we will get the least P1 or not, because V1 is the exit velocity of water, which is a constant, and H is the height of draft tube, which is also constant, and Pa is also constant. So moreover the pressure at point 1 will depend upon how much less the V2 is and how much less the HF is. So it means that P1, the pressure at point 1, will greatly depend upon V1 square by 2g minus V2 square by 2g minus HF. Since I have told that V1 is constant, so greatly depend upon what? V2 and HF. So lesser the V2 is, okay, and lesser the HF is, we will get the minimum pressure at point 1. Okay, because V2 is least, then V1 square by 2g minus V2 square by 2g will be more than, and in case HF is also least, in that case the quantity which is inside this bracket will even greater. So greater amount will be subtracted from Pa, we will get least P1. It is like this. So ideal vacuum would be in the case when V2 is exactly equal to 0 and there is no HF. So ideally the vacuum pressure exerted over point 1 will be the case in which V2 is equals to 0 and there is no HF, so that is equals to V1 square by 2g. Therefore ideal pressure will be the case when V2 and HF both are 0, so V1 square by 2g. Thus practically the P1 depends upon V1 square by 2g minus V2 square by 2g minus HF. So this is what the practically on which the P1 will depend. Ideally the maximum vacuum will be created in case V2 and HF is 0. So this is the ideal case, V1 square by 2g, and this is the practical case. So this ratio is what called as the draft. So hope you would have understood that why draft tube is implanted over the exit of an hydraulic turbine. So in short, it increases the work output of the runner. So it is like this. Suppose this is the dam and from the penstock the water is reaching the runner. Ultimately we are using a draft tube. Suppose the height of draft tube is H. So what happens, that gross head of water would be, this is the dam, so this is the water top surface, and up to the bottom we can add this head also, this draft tube head also. So net head would be more in case we are using the draft tube. In case we are not using the draft tube, means water is just exiting out and going to the tail race without any draft tube, in that case the head would be without this head, means this much head would be lessened. In this case only A to this much head, means H is subtracted, only this much head would be available in case we are not using draft tube. So hope you would have understood the purpose of draft tube and efficiency of draft tube. Thank you.